Hello, so how are you? So thank you for watching, and I'm sorry that uh, today's class we still use the video lecture because I still do not have my glass and my eye is. But anyway, thank you. I hope next week everything will be returned to normal. I'm really sorry, and I thank you for your kindness and your understanding. Okay, so we just had our second exam. So second exam is about one sample problems. Okay, ah, so I check your exam. I find most of you, many of you, all of you did a good job. So I feel really happy, and I hope you can keep your excellence and get a good grades. Yeah. Okay, so this means like you understand those material very well, so that's good. So one sample problem, we say just have two parts, like estimation or confidence interval, mm, uh, and the other one is testing, right? Estimation and testing. So confidence interval we just use as formulas. Okay, so by now we say understand so you apply the formula is easy, right? We just a little bit confusing thing is this star t star, and for hypothesis testing is also like this, like just you should know t check t table or z table, right? So the process for testing uh, testing is the first one is the hypothesis. The HO hypothesis is mu equal, right? Mu equal this number. This number can be population's average. So HA can be three options, right? Mu not equal, or more specifically can be larger than or less than. So which one we should choose? It's up to us, right? We should check this is determined by what the good meanings. So one side is good, or a close is good. So we have one tail test and a two tail test, right? And also more specifically, if we use z value or z table, we have one tail z test, and we have like one tail or two tail t-test, right? So we just find this test statistic. You say we call this test statistic. Then we just determine this value is big, this number is big or small, right? We just determine this number test statistic is big or small. So to determine this test statistic is big or small, we have two ways. Like compare p-value with alpha. And the other way is just compare the test statistic, this number with critical value. Okay? So we compare z value with critical z value. And this t value was a critical t value or t critical value. So where those critical value come from? From so z table or t table, right? So your decision is if this we find if the test statistic is big, then we say oh difference is big, right? If this test statistic is not so big, it's small, then we say the difference is small. If difference small, then we just accept HO, right? So mu equals mu equals this number, mu equal mu 0 is okay, right? Is acceptable. Okay, so this is one sample problem. Okay, so now once we have one sample problem, so we have two sample problem and many sample problems, right? So today's topic is a two sample problems. Okay, so what are the two sample problems? So let's check some examples. Let's say like two sample is like we have two set of data. We say like here sample this is sample 1 data or sample 2 data. Okay, like sample 1 data, sample 2 data. Okay, so if we have two, then we want to compare. The typical question is like, is this method, is this treatment better than other treatment? Or treatment A is better than treatment B? Or if we have two classes, can we say class 2 or this class performance better than other class? Okay, so we say, so if we have two samples, the two sample problem usually is comparison. So if we have two samples or many samples, we just want to compare, right? We want to compare whether this is better than others, or if we have many, then we try to find the best one, right? So if we want to try to find the best one, at first we need to compare. Okay, so how can we conduct those comparison? So we say the foundation is again is those things, sampling distribution. So from a population, take sample, then we have the sample mean follow this normal, right? Okay, so this is important. So now let's say for two sample problems is just from two populations we take sample. Like here, from this population take a sample, from this population take a sample. So for this population, mean is mu1 and standard deviation sigma 1. For this population, average is mu2 and standard deviation sigma 2. Okay, so from this population take a sample, from this population take a sample. So we say sample mean x bar, suppose this is y bar. So this x bar and y bar follow this normal, right? So x bar follow this normal, which means in mu1 sigma 1 over square root of n1. Suppose the sample size n1 and the other sample sample size n2. So this y bar follow this normal. Okay. So this is just the central limit theorem and the sampling distribution, right? Okay. So now we say that normal minus normal is still normal. So we have this result. Normal minus normal is still a normal. So normal minus normal still normal. So mean is mu1 minus mu2. But for standard deviation, we cannot use this standard deviation minus that standard deviation. We cannot use this. Cannot use minus. Standard deviation never can be used minus. So why? Because let's say like standard deviation sigma 1, sigma means change, right? So suppose this data or have sigma 1, this data have sigma 2. Suppose sigma 1, sigma 2 the same. Okay, so we say they have the same changement. So if we put them together, okay, so we get this like this, right? So what is the variance? The variance equals us mu1 minus mu2. So definitely not, because by now if sigma 1, sigma 2 equals this equals 0, right? So 0 means no change at all. So put the two things. This have change, this also have change. Put together, no change. Make no sense. Still have some changement. Okay. So actually, we say put together. Standard deviation cannot use minus. And for variance, suppose there's sigma 1 square, there's sigma 2 square variance. We say we have this result. Variance can be added them up. So variance plus. Okay, so let's say that this variance is sigma 1 square over n1. This variance sigma 2 square over n2. So we have this. So variance is added them up. Then for normal distribution, we focus on standard deviation. So we use square root. So we have this result. We say x bar minus y bar follow this normal. The mean is this, standard deviation is this. Then we continue to standard normal, right? So this minus the mu divided by sigma follow standard normal. Okay? So this result just from centrally limit theorem, right? Okay, so now we start from here. We say those things follow standard normal. Okay. Okay. So our purpose for two sample problems is comparison. So usually we will convert the comparison problem as a testing problem. Okay, so we compare what? Usually compare the mu, the average, right? Mu1, so here we say mu1, mu2. Mu1, mu2 quite the same, or mu1 not the same, or more specifically, can mu1 larger than mu2, or mu1 less than mu2. So here HO is equal, mu1 equal mu2, means there's two methods or two classes have no significant difference. And HA so have difference, or more specifically, or this is better than that. Like mu1 is larger than mu2, or mu1 less than mu2. Or simply like mu1 mu2 not the same. So here, again, we have three options for HA. So which one we should pick? One side or two sides? This depends on the question. What we want to say. If we wanted to say like class 1 is better than class 2, we should use mu1 larger than mu2, right? If we just check whether there's two group of people have difference or no difference, we don't care which is high. We just say they are the same or not the same. Maybe we can use mu1 not equal mu2, right? mu1 equal mu2 was mu1 not equal mu2, right? So this is just like one sample problem. HA, which HA we should pick depends on our purpose, right? What we want to say or depends on the problem. What good meanings, right? Okay. So let's say that under HO, if HO is true, if mu1 equal mu2, then this part becomes 0, right? Okay. So we have this value. We say z equal x bar minus y bar over the square root of this follow standard normal. Okay. Okay. So we say under HO we have this result. So we know this thing follows standard normal. Okay, so just by now we say just like one sample problem, we don't know sigma 1, sigma 2. If we know sigma 1, sigma 2, then these things follow exactly standard normal, right? So if we know sigma 1, sigma 2, so we can find this value. So we can call this value z value. Then determine this z value is big or small. We can check it with z table, right? Okay, but the question is we don't know sigma 1, sigma 2. Those are population standard deviation. We don't know. So we only know is standard deviation from sample. We know S1, S2, right? So here S1 is standard deviation from sample 1, S2 standard deviation from sample 2. So we can replace sigma 1, sigma 2 by S1, S2. So we get this value. We can use this as our test statistic. Okay, so we can easily do our calculation, right? Find this number. So the question now is we need to determine this number is a big number or small number. So if there's a big number, we say, oh, there's two groups have a difference. If this number is not so big or small, then we say, oh, difference is small. We can believe there's two group or two classes or two group or two methods have no significant difference. So we say the question is, we can easily find it because the question is, how can we determine this number is a big number or small number? So we need to find a p-value, or we need to check a critical value. But here we have a question of which table we should check, C table or T table. Okay, so so here we have this big questions. C table, T table depends on these things follow which distribution. If follow normal distributions, then Z table, right? If we follow T distribution, T table. So the question is which distributions this standard, this test statistic, or these things follow. Okay, so this is the question. So what is the answer for this question? So we say the exact answer for this question is tough. Is quite complicated. So we can only say these things roughly these things follow T distribution or close to T distribution. So for T distribution, what is the degree of freedom? So the exact formula for degree of freedom is also very complicated. So make things simple, we just pick this as degree of freedom. Like we have two samples, and then we have two degree of freedom, right? Sample size n minus 1. We know for one sample problem, degree of freedom is n minus 1. So here we have 2n, right? So here we have two degree of freedom, like n1 minus 1, n2 minus 1. Then we just pick a smaller one. So here, smaller one, or why we pick a smaller one? Why we will not pick this maximum one? Why we just pick smaller one? We say, why this not? This one, why not? Okay, so we say instead we say if sample size is big, then we have like a more if the data is big, or if we sample size is big, then we have more information about the population, right? If sample size, let's say, if sample size is very big, then sample become population, right? So instead, there's a common sense. If n is big, sample size is big, then we have more precise information, or we can say big is bad. Big is bad. Big one is bad. Okay. So it seems like we should pick a bigger one, maximum, right? But the story is sample size big, and so we can say that big means good, then smaller means not so good, right? So here, if we have two sample size, we just pick smaller one, means we just check worst case, right? We just check worst case. Or we just are more conservative in making one decision. Okay, so we just pick smaller one. Okay. So if we regard these things follow tedious distribution, then we just check a t-table. Then we can find this number big or small. Then we can make a decision, right? Okay. So now let's consider the problem. Okay. So now suppose we have two sections for Math2526. We use the same exam, and so we have this result like class 1 average is 84, class 2 average is 81. So we have evidence that we know this is better than this. We have evidence that class 1 perform better than class 2 in this exam. Okay, so the question is, can we this evidence is statistically strong enough? Can we say, like, can I say, suppose I teach class 1, other professor teach class 2, so I really wanted to say my teaching is better than other guy, right? Or my class perform significantly better than other class. So I wanted to say that, but statistically we wanted to sure, like, can we say, or can I say class 1 performance significantly better than class 2 at this significance level? So we have evidence, but instead we just check the significance, whether this evidence is strong enough. So how can we answer this question? So we say we just treating this as a testing problem. So first step, we just set the hypothesis. So it shows no difference, or not so significant. So mu1 equal mu2. And HA, so here very clear, we should have said mu1 larger than mu2, right? I just wanted to prove mu1 is better than, larger than, higher than mu2. Okay. Okay. So then calculate test the statistic. So this is t-value x bar minus y bar is 1 square over n1 plus s2 square over n2. So put those things. So x bar is 84, y bar 81. So what is s1 square? So this is a standard deviation. Like for class 1, we have 25 students. Average 84, standard deviation 7. So class 2 is student 20 students, average 81, standard deviation 9. So we just plug in here, then a little bit of calculation, we find this number. Excuse me. Excuse me. Oh, we need to do a little bit of calculation. So this is easy. But anyway, like let me do this and need to calculate. Okay. So this equal 49 over 25. I'm sorry. 49 over 25 plus 1 over 20. Okay. Okay. I found this equal 1.22, right? Yeah, I think 1.22. Yeah. Okay. Okay, so now we need to check this number is a big number or small number. 1.22 is big or small number. So we just compare this number with t critical value. So because it's a t value, so we need to check t critical value. So this t critical value is from t table. So for t table, at first we need to determine degree of freedom, right? So what is the degree of freedom? Here, degree of freedom. Let's say, so we have n is 25, 24. Oh no, 25, 20. So we have 2 degree of freedom is 24 and 19, right? So we should we just check a smaller one. So we just use 19. Okay. And the 1 tail, 2 tail. So let's say this is 1 tail because we're talking about exam score. So high is good. So we just check a 1 tail, right? So there's a 1 tail. Okay. 1 tail. So what is alpha? Alpha is 0.05, I think, right? Significance level alpha 0.05. So use this degree of freedom 19, 1 tail, 0.05. So we can find the critical value. So let's check a t table. So degree of freedom 19. Okay, this line and 1 tail 0.05. So 1 tail 0.05. So I just check this, right? 1 tail 0.05. And then this cut point I found is thus, like 1.729. 1.729. So this is a critical value. So we use this to judge other numbers big or small. So 1.729. Okay. So 1.729. So use this as standard. So we can say this is 1.22 is small. Right? Okay. So this critical point just like that. We just check out from 0. So this critical point 1.729. So those numbers small, right? Okay. So this 1.22, we can say this is small. Small number means the difference is not so big. And then go back to the question. We say this Can we say class 1 perform better than class 2? Significantly better than class 2? Our, our conclusion is no. These two classes is essentially quite the same. Okay? So we also can say like 3 points difference is not so big. We still regard this as a small difference. Okay? Okay. So we say there's a 2 sample problem. So we say oh those kind of problem quite the same as 1 sample problem. Just to find the cut-off point or test the statistic, then determine big or small. Right? So now let's consider this problem. We want to compare two percentages or proportions. Like here we have 2 candidates. Okay, so we want to determine who is more popular or who will win the election. Okay, okay. So let's say we just do 2 surveys. So we check 1,000 people and find so many people like A. So we have this percentage proportion for candidate A is thus 42, right? 42%. And for B, we check 2,000 people, find 9 people like B. So we find percentage for B is 45, right? Yeah. Okay. So here from our survey, we find B is more popular, have 3%, 3 points, right? More than candidate A. So we have evidence B is more popular. But again, we need to check whether this difference is significant. Okay, so we just check significance. Like we have evidence saying we just check significance, whether this evidence is strong enough. Okay, so we just change this as a testing problem. So HO is P1, P2. So here P1 PA, PB. So we just change the P1, P1, P2. These 2 people popularity is quite the same. And so HA, so we choose this, right? We say candidate A is significant less than candidate B, or P1 less than PB, right? Okay. Then for test statistic, so we just use this formula x bar minus y bar. So in here, this PA hat, PB hat, just x bar, y bar, right? So we use this x bar minus y bar, and it's 1 square in 1 is 2 square in 2. So x bar is 42, 0.42 minus 0.45. So here is 1 square. We can use PQ, right? Oh, it's 1 square. Oh, no, sorry. P1 Q1. Okay. So here hat, right? So we just use that. So it's 1 square is 0.42 multiply 58 divided 1,000. So 45 PQ over N, right? Yeah. Okay, so we find this number. So we say there's a T value or Z value. Should we check a Z table, T table? So this one, we say the Z value, because sample size is quite big, right? So Z value. Okay, so for Z value, so we have the cut point. So now we check Z table. We say the cut point 1.57. So we can, for Z table, we can find exact probability. We can find a p-value, right? We also can find a critical value, right? So this 1.57, negative 1.57 is big number, small number, or close to 0 or not so close to 0. So we can find a p-value. So let's say, what is p-value? So p-value is this probability, right? C less than negative 1.57. So we check, so check Z table. So we just check positive 1.57, right? Then use 1 minus. So let's check Z table. Okay, Z table. Yeah, here Z table. So we check 1.57. Yeah, okay. 1.57. I think it's this number, right? 1.57. Then we should 1 minus 9418. So this is p-value, right? So this equal 0.582. Okay. So this is p-value 0.0582. So we just go back with the p-value equal 0.0582. Okay, so now we check this p-value is big, p-value or small. This number is big or small. So we just compare with alpha. So what is alpha? What is significance level here? Okay, so the question, no significance level. So we say if do not specify the significance level, then we say by default we set alpha as 0.05. Okay. If we have the significance level, then we just use this. If we do not have, then we just use this by default, right? 0.05. Okay. So if alpha is 0.05, then we say, oh, this p-value is larger than 0.05. Then our conclusion is p-value is large, then means close, right? Means this number is small or close to 0. So we can say we will believe the difference is small. Or we can say like the difference is small, and so like a 3% difference is not so big. So we still believe there's two candidates have the same chance to win the election, like that. Okay. Okay. So this is we use p-value to make our decision. So the other way we also wanted to check the other way is we just determine this is 1.57 is big number or small number. So here to determine this, we just find z critical value. We just find z critical value. Okay, we find this. So how can we find this critical value? We say we just check z table. Okay, so z, and what we want to find is this cut point such that this is 0.05. Okay, so this number is critical value. Okay. Okay, so how can we find this? So let's say we just check the positive part. So this is 0.05. Okay, so what is this cut point? So we say this 0, 0, 5, then all the way down is 95. So we need to check this 9500, right? Okay. So find the neighborhood, then we find the cutoff point. So I remember this is just 1.64 or 1.65, or more precisely, this is 1.645. Okay. Okay. So let's check it. Let's see. So this is the critical value. Right? So let's go back. Let's confirm this. So how can you find this number? So we check 9500. So 9500 is here, right? 9500. Okay. Okay. So this the critical value is thus one. So this the critical value is negative 1.645, right? So we can say like we use this negative 1.645, use this to determine those numbers close to 0 or not so close to 0. So our numbers here, negative 1.57. So we say negative 1.57. We can believe this is close to 0, right? So again, so we get to the same conclusion. The difference is not so big. Difference is small. Okay. Okay. So we have many of those kind of problems. So we say, so the kind of problem quite the same. Like if we have two samples, then we can find a sample mean, a sample size, sample mean, and the sample standard deviation, like this. So let's check this problem. Okay, so let's say that here the story is we wanted to compare the two companies' customer certification level. So we just do a survey. So this survey is not a yes or no question. We survey ask customer to give points. Like, so 1, 2, 3, 4, 5, right? So 5 means most certification. So like from these 5 numbers, which number you will choose? Maybe you will choose 5, maybe you will choose 3, right? Then we put all those numbers together, so we find the average. So for company A is 3.51, for company B is 3.24. So those are average. And that was the standard deviation. So, okay. So now, so again, let's start quite the same. Like we have the evidence very clear, like 3.51 is larger than 3.24. So it seems company A's service, customer service is better than company B. Then we wanted to check whether this difference is significant, right? Significant. So we just converted those to testing problem. So first one, set a hypothesis. You say, so HO is no difference, right? HA here again, like we just one side, right? HA is have this is better than that. So here we check. So let's say that you also consider this like HA as this, like HA is mu1 not equal mu2. You say they are the same. The two companies the same or not the same. But in this example, maybe we will choose this make more sense. We want to compare, we want to say company A is better than company B, right? We don't care whether they're quite the same or not the same, right? So maybe like if you choose this one is also okay, but this one make more sense, right? So compare this, so we should choose this. So again, what HA is actually up to us. What is our purpose? Okay. Okay, so then and to find the test statistic, so use this, right? So x bar minus y bar over x1 square in 1 is 2 square over in 2. Okay, so after some calculation, we find this number is this 5.684. So this is z value or t value? Z value or t value? So we say logically this should be t value, but in here z value t value doesn't matter because the sample size is quite big, right? So we also can use the z value. So no matter this t value or z value, so we can determine this is a big number because let's say for standard normal, okay, 0. 3 is big number, okay? So this is big, this is big. So for t, quite the same, right? So this is 5, almost 6. So this is a huge number. This is a huge number means the difference, huge difference. Okay? So we say, oh, company A is significant better than company B. Okay? Okay. So our decision is very clear, right? Okay, so let's say we stop here, then continue. Okay, so because yeah, the video are just about 50 minutes. So I also need to take a rest for my eyes. Okay.